Welcome back to AI.Code.Cast. Today, we're going to be doing a deep dive into this problem that's all about timing. Like literally, it's called number of flowers in full bloom. And basically, we have to figure out how many flowers are like in full bloom when people visit a garden.
Yeah, it's a classic problem, It really
Uh,
makes you think about efficiency and how to handle data that's, well, changing over time.
exactly. So imagine like you have this garden and there's all types of flowers, but they all bloom at different times. Some might bloom for a whole week, others just a couple of days. And they all have these different start and end dates. Now people are visiting this garden on certain days, and we got to figure out how many flowers each person sees when they're, fully bloomed.
It's almost like you're trying to plan a party where everyone's coming and going at totally different times, and you want to know, how many people are there at any given time?
That's a perfect way to put it. So let's say we have this list, right? It has all the flowers and when they bloom with a start and end day for each one. And then we have another list of when each person is visiting the garden. Our mission is to basically write code that can figure out how many flowers are in full bloom for each visitor, but do it quickly, efficiently.
So where should we start with this?
Well, I kind of just want to go through each visitor one by one and then check every single flower to see if it's blooming on that day.
Yeah, that's the brute force approach, and it's a natural place to start, I guess. You're basically using, nested loops, to compare each visitor's day with every flower's bloom time.
But I'm already seeing some problems with this. Like, what if we have a ton of flowers and visitors? Thousands? Maybe even more? It'll take forever to run that code, won't it?
You're totally right. That brute force method gets super slow as the data gets bigger. Think about it, if you've got 10,000 flowers and 1,000 visitors, that's like 10 million comparisons.
Okay, so brute force is out. What if we try to be a little clever? Can we organize the information better so the calculations are faster?
Yeah, that's where sorting comes in. What if we sort those bloom times in a way that helps us find the right info for each visitor super fast?
Sorting usually makes searching faster, yeah. But how exactly would we sort them just by start date?
That's a good start, but we also need those end dates, right? What if we make two sorted lists? One for the flower start times and one for the flower end times.
Okay, two lists. I'm listening. Why would that help?
Think about it. If we know how many flowers have started blooming before someone arrives, and we know how many have already finished blooming by then, we can easily get how many are in full bloom at that exact time.
Ah, I see. It's like we're finding the exact window of time when a visitor is there and only counting the flowers blooming in that window. But how do we actually use these two lists to do that?
That's where the magic of binary search comes in. We can use that on both of our sorted lists to zoom in on the info we need for each visitor.
Wait, hold on. Binary search. I remember that from like forever ago. How does it work again?
Okay, imagine you're trying to find a word in a dictionary. You don't just flip through every page, right? You open it somewhere in the middle. See if the word's before or after that page. Then you keep cutting your search in half until you find it. That's basically binary search. You keep getting rid of half the possibilities until you're left with what you want.
Right, right. It's all about those smart comparisons. Okay, so we'd use that on our flower lists. But what are we searching for exactly?
Good question. Okay, let's say someone visits on day 5. We'd first do a binary search on the list of start times to see where the first flower that blooms after day 5 is. That tells us how many flowers started before or on day 5.
Okay, I get that. And then we do the same with the end times.
You got it. We search for the first flower that ends on or after day 5. That tells us how many flowers ended before day 5.
So if you subtract that second number from the first number, you get the number that are blooming on day 5. Like that's how you define that window we were talking about.
Exactly. We're basically picking out only the flowers that started before or on day 5 and haven't finished yet.
That's pretty clever. We turned a whole bunch of comparisons into just two quick searches.
It really shows you how, just sorting the data can unlock so many faster ways to find what you need. And binary search. Yeah, that's a super useful trick to have up your sleeve, especially for stuff like this.
It's crazy how sorting can make such a big difference. But okay, let's actually get into how we'd code this whole optimized binary search thing. What would that look like?
Well, instead of writing out the actual code, maybe we can talk through the steps, like in plain English. Almost like pseudocode, a high-level view, without getting lost in the details.
I like that, like a recipe. What are the ingredients and how do we cook up this solution?
Okay, so first, we need our input, right? The list of all those flower times and when the visitors show up. Then we make those two sorted arrays we talked about, one for the flower starts and one for the ends. We can use any sorting thing we want for this, but it's good to pick one that's fast when you have a ton of data.
Okay, so sorting is step one. Then what?
Then, for each visitor and their arrival day, we do those two binary searches. On the start times array, we want the index of the first flower that starts blooming after the visitor arrives.
So let's say they arrive on day 5, and the search finds a flower starting on day 6 at, like, index 3. That means 3 flowers started before or on day 5.
Exactly. Then we do the same thing on the end times array. Find the first one that ends on or after day 5.
Okay. Let's say that search finds a flower ending on day 5, right on the dot at index 1. What does that tell us?
That means one flower finished blooming before day 5, and now. The grand finale, we subtract that end time index, the one from the start time index, the 3. Boom, 2. That's how many flowers are in bloom on day 5.
Got it. That makes sense. It's really neat how you use those sorted arrays in the search to pinpoint the exact answer.
Yeah.
But are there, like, other ways to solve this, maybe using totally different ideas?
There are actually a couple more that are worth checking out. One is the difference array approach.
Difference array. That sounds kind of cool. What's that all about?
Okay, so instead of storing like the actual number of flowers blooming each day, what if we stored the change from one day to the next, like how many more or fewer are blooming? That's our difference array.
So it's like tracking those little changes each day, how many new ones bloom and how many finish up.
Yeah.
But how does that help us count the flowers for our visitors?
Well, with this difference array, we can build something called a prefix sum array. Each spot in that array tells us the total number of flowers in bloom up to that day.
So we're basically rebuilding the actual count for each day, even though we're only storing the changes. That's pretty clever.
Yeah, it is. And once we have this prefix sum array, it's super easy to find how many flowers are blooming on any day. Just look at the value at that day's index.
Okay, I think I'm following.
Yeah.
But how do we actually make these difference in prefix sum arrays in the first place? What does that process look like?
Let's break it down. We start with our difference array, all zeros, because at the very beginning, no flowers are blooming. Then, for each flower, we bump up the value at the index for its start day, and we lower the value at the index after its end day.
So if a flower blooms from, say, day 3 to day 7, we'd increase the value at index 3 and lower the value at index 8.
Exactly. That's how we mark the start and end of each flower's bloom in the difference array. Then, to get that prefix sum array, we go through the difference array and keep adding up the changes as we go.
So each spot in the prefix sum array is the total of all the changes that came before it.
Right. It gives us that running count of how many flowers are blooming on each day.
This whole difference array thing seems really efficient for keeping track of those changes.
Mm-hmm.
But remind me, how do we actually use it to answer our original question? How many flowers does each visitor see?
Well, that prefix sum array already has the total count for each day. So to get the answer for a visitor arriving on, say, day 5, we just look up the value at index 5 in that prefix sum array.
Oh, that's right. It already tells us. But wait, I thought we were going to use binary search again. Does it fit in here somewhere?
You're right, we can still use it, but in a slightly different way. If we have like a ton of visitors, we can use binary search to quickly find the right spot in that prefix sum array for each visitor's arrival day.
I get it. We're not searching for a specific value this time, but for the index that matches the day. Makes sense.
It's all about using the right tool at the right time, right? Binary search is perfect when we have sorted data and need to find something fast.
Okay, so we've got two pretty cool approaches so far. This optimized binary search, and then the difference array with prefix sums. Both way faster than that brute force thing we were talking about earlier. Any more tricks up your sleeve?
Actually, there's one more we haven't talked about yet, the sweep line algorithm. It's a totally different way to think about and solve this whole problem.
Sweep line. I'm picturing like a line sweeping across the garden and counting the flowers.
Yeah, that's a great way to visualize it. Imagine a line moving across a timeline that shows all the days. This line, our sweep line, keeps track of how many flowers are blooming at any moment.
So it's like this moving window that shows us what the garden looks like right now.
Exactly. And every time the sweep line hits the start of a flower's bloom, it adds 1 to the count. When it hits the end of a bloom, it subtracts 1.
Okay, so it's counting up and down as it goes.
Yeah.
But how do we know how many flowers each person sees?
When the sweep line hits the moment a visitor arrives, whatever count it's holding, that's how many flowers are blooming right then. It's like the sweep line takes a snapshot of the garden at that exact moment.
I really like how visual this is. I can almost see those flowers popping up and wilting away as the line moves across.
It's a really neat way to think about it, and it turns out it's pretty efficient to code too.
So how would we code this sweep line algorithm? What are the steps?
The trick is to think of everything as a point on that timeline, when the flowers start, when they end, and when the visitors arrive. We got to sort all those points in order, chronologically.
So instead of separate lists for flowers and visitors, we're putting it all together on one big timeline.
Exactly. And then our sweep line can just move across it from left to right, dealing with each point one by one.
Okay, so when it hits a flower start, it adds to the count. When it hits a flower end, it subtracts. And when it hits a visitor, it writes down whatever the current count is. That's their answer.
You got it. It's a really organized way to handle all that info and keep track of what's blooming and what's not.
I'm really liking this sweep line thing. But in the code, how do we actually represent all these points? Do we need like a fancy data structure or something?
We could, but even a simple list would work. Each item in the list is one of those points, and it tells us what type it is: flower start, flower end, visitor arrival, and what day it happens. We can even add more info if we need to, like which flower it is.
So we'd sort that list by the day, and then our sweep line code can just go through it one by one. Not too bad.
Yep. And the cool thing about Sweepline is that it can be used for all sorts of problems, not just flowers. Anytime you have things happening at different times, you can use this idea.
This is awesome. So we talked about 3 really cool solutions today that optimized binary search, the difference array with prefix sums, and then this sweep line algorithm. It's amazing how there are so many ways to solve the same problem, and they all have their own clever tricks.
Yeah, and each one shows you a different part of coding, right? Optimized binary search is all about getting your data ready and then searching it super fast. Difference arrays are about storing data in a smart way so the math is easier. And Sweepline, that's all about visualizing the problem and breaking it down into steps.
It's like you have a toolbox full of different tools, and a good coder knows which one to grab.
Exactly. That's what I love about coding. It's not just writing code, it's about finding creative ways to solve problems.
So, to all our listeners out there, I have a little challenge for you. What if we didn't just want to count the flowers? What if we wanted a list of all the specific flowers that are blooming when each visitor arrives? How would you change these algorithms to do that?
Ooh, that's a good one. It makes things trickier, but I think those main ideas we talked about would still work. We might need to tweak how we store the data and make the algorithms give back lists of flowers instead of just numbers. But yeah, those ideas of sorting, searching, and handling events efficiently, still totally relevant.
It's a fun challenge to try out. Share your solutions and ideas on the AI.Code.Cast forum. We always love to see what you come up with.
Definitely. Always great to see how everyone approaches these problems.
Well, that's it for today's episode of AI.Code.Cast. Big thanks to our expert Jess. It's been awesome having you.
Happy to be here and always fun talking code with everyone.
And to all our listeners, thanks for joining us on this deep dive. Keep coding, keep learning, and we'll catch you on the next AI.Code.Cast.